So also a hello from my side. And yeah, thank you very much for the invitation and the possibility. And I'm just looking, yeah.
Unmute your microphone, please.
Can you hear me now?
Yeah, sure.
Yes.
Yeah. Thank you. So did you hear anything I was talking, or was there?
Go back.
It's better to repeat.
So I start all over again. Yeah, the presentation topic for today is self-supervised learning for computer vision, because I was recently exploring the topic. And especially I want to talk about like 3 of the state-of-the-art techniques. This is called SimCLR, MoCo, and SWAV. And we will also have a look into the future. And yeah, before I start with the setups, I want to start with what is supervised learning and self-supervised learning, and why it is very interesting for us and even for computer vision applications. And then I will move on to these 3 setups and then to the future outlook, and then we have time for discussion and general questions. So supervised learning is the traditional setup. This is what we usually do when we build a model. We have our data, we have our input data and our labels, like the famous dog and cat image example, where we have the label dog and the cat label to it, and then we build our model with that. Whereas with the self-supervised learning, we have unlabeled data, and we need a special learning objective so that the model can learn a good representation of the data. And with this, when the model can learn this representation of the data, we can then use the model in the next step to train it also in a supervised way and leverage this representation to get better results. At least that's the idea behind it. And yeah, this is like a nice overview picture where you see here on the left side the supervised learning approach, where the labels are color-coded. And you can think about the unsupervised setup, that the model somehow gets hold on the structure of the data, what is like shown here, that there maybe are 2 groups, and the model learns how those groups are related to each other, and then maybe this information can be leveraged later on in a supervised task. So that's the idea behind it. And on the presentation, you find all the sources below, so don't worry if you don't can write it down. We will also distribute the slides later, and there you have all the links. And yeah, and I found this slide very interesting. It's from Jan LeCun, and it's a little bit about how much information is needed for learning. And I like this different approaches. And for example, with pure reinforced learning, you get very sparse feedback, just a few bits of information. With the supervised approach, it's a little bit more. But interestingly, with the self-supervised approach, at least the idea is, because yeah, this is not like 100% truth, of course. The idea behind is that you get a lot more information that the model can take up and catch up, and this can be then leveraged for the downstream tasks. And yeah, and this is here like the traditional self-supervised learning setup. And in the end, we want to pretend that we don't know something from the input and try to predict that. So this can be with time series data that we input the past, the model has to predict the future, or that we predict only some parts, maybe which are visible or not visible. And this is here more into the computer vision direction, that we occlude, mask, or corrupt a part of the data. So this can be that we draw boxes around specific parts of the image in a randomly way, or mask out specific parts, add some noise or random cropping. And this is applicable for computer vision. And this reconstruction task is one possibility to set up also our self-supervised learning approach. And yeah, And we will focus on these three setups I have mentioned before. And self-supervised learning is not like a very new thing. This has like a history. And for the history, I can really recommend this blog post down here. It has, I guess, like 20 methods plus, which were developed over a couple of years. And sometimes this can be interesting if you have a special problem and maybe you find some nice inspiration there. But usually for the computer vision tasks, the methods I present then later on are the way to go because they're quite elegant and quite powerful. Yeah, but before we dig into that, I want to show you like a basic classification of self-supervised learning. One big group is the generative approach, and this is what is there for quite a long time. And I guess the most famous example are autoencoders, and autoencoders are models where you feed in your data and you try to predict it, and the network has to learn like a representation. Another nice example is colorization, where you feed in your grayscale image and try to predict the colors again. And those are example tasks where the model has to pick up like a representation of the data, and that can be leveraged later. And one important thing here is that we measure our loss, the loss for training and adapting our model on the output space, so in the pixel space. Because we measure then here for colorization, for example, yeah, how are those colors correct when we compare it to the real data, or when we have to reconstruct an image, does in an autoencoder does the output look like the input? And another setup which was gaining a lot of traction in the last year is the contrastive approach, and this is a very elegant way. And we will also see later on how this is then leveraged. But the basic setup is that we feed in 2 data points in the most basic setup, and the model has to learn if those 2 data points are similar or not. So this is a little bit different from here, and the loss is measured then in representation space. So we feed in our data, get a vector output, and those vector output should be similar for similar inputs and should be dissimilar for dissimilar inputs. And this is the setup which is used by the SIM-CLR approach, the MoCo, and the SWAV approach. And I guess to make it a little bit more easy to visualize, I have here an example. And because I guess when you hear it the first time, it's a little bit tricky when I say, what are the input data or how does it look like? So the usual approach is we have here an image of a dog, an input data point, and then we generate something which is always or most often called a view of the image, and this is a transformed image. So we have here like a transformed to grayscale. Here we shifted the color a little bit, and those are our 2 data points. And then we run that through our network. Usually the networks consist of a convolutional neural network, and then of a special head, which is here abbreviated with multi-layer perceptron, but don't worry. In the end, what the network is doing, we feed in the image and we get a vector. And we want that for similar parts of the image, because this is here a dog, this is still a dog. So this vector should represent the dog, like almost similar, will be not 100% all the time, but it should be very close. And when we feed in then another image, like this chair, we do the similar approach, generate 2 augmented views, run it through the network, and then we get also similar vectors here, but they should be dissimilar to here. And one important note is, because when I saw it the first time, this was not obvious to me, but it's always the same network. So we leverage always the same network to generate our vector representation. And before we dig into the setups, just one slide about the loss function, because this is like the heart at the end of the training. But don't worry about the math. Yeah, we use a softmax classifier, but in the end, what we do with the softmax losses, or what we want, is to calculate the score between our positive example. So this is in our case x, and x plus is like the positive pair to it, and this score should be bigger than the score between our positive example x and another negative example. So this pair should be similar, this should be dissimilar. And this is achieved by this big formula, but in the end, this is the softmax classifier we usually use. And the only difference here is this small t for transpose, which is our scoring function in this case, and this is the dot product. So, and in the end, this is just meaning that we get here a value of 1 if those two vectors are similar, and if our network is properly trained, these vectors should be similar. Like for the cat and dog example, if we have here a dog and here a dog, it should be close to 1. Whereas if you have here a dog and here a cat, it should be close to 0. And this whole term then should go to 1 divided by 1. But don't worry about the math. I guess later on we have a nice figures to get more intuition how this works. And there are some interesting papers that found that this kind of optimization loss is maximizing the mutual information, which is kind of a measure about the information content between the inputs. So, and with that, we're equipped to look at the first setup, which is called SimCLR. And this is now the scheme. We have here our input image again, our two views, so our augmented views of the input image. Then this is our network again, and the output head, and we want to maximize agreement. And this is what you have seen before, but now animated. And you see here, we want to get those vector representations from the similar image close to each other. And we want to make the other objects in vector space to push away, so that it's, those views have here a similar vector, and this vector should be similar to other views of other inputs. And there are even two versions of the paper, or the version 1 is like how this all started, getting traction in the community, this contrastive self-supervised learning. And the version 2 is like an extended version where they also do a little bit of model distillation. But yeah, the first paper is like having the details for this setup. And what they found is they need more, or they need a lot of data augmentation, more than maybe what you usually use in a normal computer vision setup. So this includes really a lot of color distortion, cutout, what you see here, special filtering. So you really want to push it to the limit that the network really learns the underlying objects. And they also use different views or different cropping. This is the right word. So this can be global and local views, which are overlapping, but also views that can be next to each other, what we have seen also before. And this was crucial to achieve here a good representation. The other thing is they didn't use it then as an output stage just a linear layer, but also a nonlinear transformation, which is quite often referred to as the output head. This was also beneficial. And what they also tested out was if they were normalizing the output vector, because the model, when they feed an image into the model, we get an output vector, and these vectors can be normalized, and they found this is beneficial. And I will also talk about that later, because I guess this is a very interesting insight, and I have some very, very nice images about that. And yeah, and the last point, of course, they found out that when you increase the patch size, meaning that you have more stuff to compare the other stuff to, a lot of images you can contrast to each other, these learned representations are better and more usable in the downstream task. And this is here the result chart. So here you see the supervised model, and you see that SimCLR is approaching that, but you need a lot of more hyperparameters for your model. And the reason behind that is because you're giving the model more information than just like one label, and the model has to like represent the data in an appropriate way, and this is why it needs more parameters to fit that. But nevertheless, a very nice result, because you don't need the labels. And yeah, now back to this feature normalization. What we usually do or what we can do at an output stage, and what they tried here is we do an L2 normalization, so that our vector has just a length of 1. And if you do that, you get all your embeddings projected to a hypersphere, so like a sphere. And you can imagine that you have similar images then close to each other, or similar classes, and classes which are far away are very dissimilar. And this is still like a topic of research, but those hyperspheres seem to be very beneficial if you then use those embeddings, so the vectors, for classifying images, because then you can like what is shown here with a linear classifier, kind of chop up the part where, in this case, when you want to classify cats, you're lucky because you just got the cats and the rest is on the other side and you're able to classify them. But this is still has to be confirmed, but this normalization of the output vectors is beneficial in a lot of cases. And for example, you also have that usually when you have a face re-identification system, like on a modern smartphone, they also use losses which are normalized, and where also your face is embedded on a hypersphere to make this re-identification process like bulletproof, that nobody else can unlock your cell phone. So this is kind of a similar way, not 100% similar, but yeah, from a high level perspective. And there's also a nice publication about that. What are those two mode of operation of this loss you have seen before? And I think it's a very nice explanation. There's one part which tries to align similar images to be close to each other. Like in this case, we have like two views of this airplane image. And in the best case, they should be very close, even though they look a little bit different, but the output space, the vectors we generate from them should be very close, because in the end, it's still an airplane, and it's even the same airplane. On the other hand, when we compare to other examples, we want uniformity, and this is like spreading out the data, because when we compare our airplane with a cat, it should not be too close, even though this is here now close, but there should be some distance in here. And this mode of operation, this comparison to the negative examples, is preserving also a high degree of information. And this is also an interesting feature we want to have. And with that, we go to the next setup, the MoCo, or momentum contrast. And in this scheme, this is now the approach from before, the SimCLR, which is also referred to as an end-to-end training setup. And what we do here is we have very large batch sizes, as I have told you before, run that through our model. So the encoder is here our model, which we feed in the image, get our vectors, those are those lines here, and then we calculate the loss. The drawback of this setup is you need a lot of GPUs, a lot of GPU RAM, in order to have high batch sizes, in order to have nice representations. And this is exactly what they wanted to address with the momentum contrast approach. They now split the model in half, or not split, but we have two models. One model, which is the same like here, which has like which is trained with backpropagation through all the examples, but with smaller batch sizes. And we set up a second model, which is not trainable like this one, so it needs less GPU RAM. And this is updated, and this is where also the name is coming from, in a momentum step. So this is the same formula you also see for the momentum optimizer. And in the end, this theta here, the symbol is here the parameters of this encoder. And M is like a number between 1 and 0. In most of the cases, 0.8 or something. And this momentum step is then we take like, I don't know, 80% of our old weights and 20% of the updated weights, which we train the normal way. And here we have a queue, and this queue is like, when we generate new negative examples, we put in here the new ones and get rid of the old ones. So this is like a memory of negative examples, but still resting on the GPU. So it's accessible during training. And because we have this kind of stepwise update of this momentum network, we ensure that the representation, like the representation of the images as vectors, is still reasonable. And because if you would not update that, of course, and we train one model, there would be a mismatch here, and this is not comparable. And this is why we need this momentum update step here. And with that setup, we have the big advantage that our batch size can be much, much smaller than what we need here. And they showed in the paper that those setups are comparable. Here you see the end-to-end approach, here the MoCo approach, and there's also this memory bank approach where the data is not sitting on the GPU anymore, but somewhere else. And this is a little bit suboptimal because it takes more time, I guess. And here you have the nice numbers. This is now SimCLR version 1 here. And yeah, from the momentum contrast, there's also a version 1 paper where they like established the principle. Then there was the SimCLR version 1 paper published. And then in the MoCo version 2 paper, they used tricks from the SimCLR version 1 paper to even get better results. And you see, this is very comparable. But the interesting part is here, they used a batch size of 4,000. And here we can only use a batch size of 256. So if you have just 1 or 2 GPUs, this could be the way to go, because this is much less burden on your GPU budget. And on top of it, it also seems to train a little bit faster. And yeah, so this was MoCo. Now, before we jump to the last contrastive paper, this is like a side note. Contrastive learning is a good thing, but the problem is without labels, there can be a mismatch, right? And the problem that maybe can arise during training is, if we have here our famous dog and cat classifier and airplane classifier, is we have this dog picture and we generate our augmented view. That there can be maybe in the negative examples we use for training, like a similar dog, which we then would count as a false negative sample, which is not true. And of course, without labels, this is kind of a tricky thing to estimate, but there are ways. And the paper shows that. But the interesting thing is, you can even do just with one positive example, and this is what we have then here, already tweak your loss function in a way that you get a high accuracy. And this is what they show here. So here you have the biased setup, which is not taking account these false negative examples. And the more negative examples you use, the more you can increase your top 1 accuracy on ImageNet, which I guess is an interesting side note. And yeah, so you see, it's like, you have to take care of a lot, because this is, of course, also, I guess in this case, what we have seen here, you would have maybe a problem if you wouldn't correct for it, if you have maybe a dog-cat classifier. I guess in a case where you go for a very similar appearance of the image, then maybe correcting for such problems when we have here a dog from a completely different view is maybe not beneficial. But this is already like touching on a philosophical point, but I guess it depends also a little bit on what your learning objective is and what you want to do later on with the model. And with that, we come to the last contrastive setup. And here you see some parts which are very similar. This is our input image. We generate our 2 views, like an orange view and then green view. This is again our model. We use the same model for both views to generate our vector. And here you see now this unit hypersphere again, what I have explained to you before. And this is a very nice visualization, because you see here the vectors. So one vector, what we get out here, looks like this. This is the orange vector, and the other one is the green vector. And this swapping assignments between views approach, or SWAV, is doing that a little bit different to what we have seen before. It does not compare the vectors directly and uses instead these prototype vectors. And those prototype vectors are just randomly initialized vectors. So they start random and we train them. So they get updated. And what we do is, like you see here, we get our 2 views, orange and green, get our vectors from the model, and then we try to find the closest prototype vector. And in the next step, we swap that. So we use the orange vector and compare it to the green one and to the output from the green view. And for the orange view, we try to, or we look at it, how close this vector is to the green one. So we swap the assignments. And we do that not just in a hard way, but we also make soft assignments. And the soft assignments gave a nice accuracy boost here. So there was work before this SWAV approach, which was doing a hard assignment, and the soft assignment was easier. So in the end, the soft assignment is meaning that we're not just looking at, like, this is the closest vector, but this is the closest vector to 80%, and this is the closest vector to 10%, and this is maybe also 10%. So it's like a little bit of a smooth assignment, you could say. And here, just to give you the difference to those to the SimCLR setup and the MoCo setup from before. So here we have our input image, generate our two views, have the same models, and then we compare just this with each other. And whereas in contrast, this is similar with the SWAV approach. We have our two views, our model, and then we compare those views with these prototype vectors. And then we generate these codes. This is what you have seen before when we look what is the closest prototype. And then we swap the prediction. So a little bit different, but still, yeah, kind of similar, but not 100%. And here you see now the animation. And yeah, don't worry if you don't understand it the first way, but it also took some time for me to get to see where the changes are. And actually this animation is really explaining the paper in a very complete way after, yeah, but the paper is quite a little bit dense in terms of math notation, but yeah, nevertheless, very interesting. So, but I guess, yeah, you see, we assign, we get the embeddings, we pick the closest prototype vectors, then switch the assignment and try to predict that. Because in the end, when the network is properly trained, those two vectors should be similar again, like what we have seen before, because it's still the same image and parts of the image should be represented by a similar vector. And this is also one thing which was developed in this SWAV paper. And the interesting thing about this multi-crop data augmentation is that this can be also used for the SimCLR approach or the MoCo approach, and helps to improve the accuracy again of those other two approaches. And in the end, the idea behind it is you generate two global views. So you take like views which have almost the whole resolution of the image contained, and then you take smaller crops. So this could be in the range like of 224, and this is in the range to, I don't know, 64, 96 pixels. And the reason behind that is you can have a lot of additional smaller views if you don't use a lot of additional global views, because yeah, they are much smaller. So the idea behind this that you have just two global views and these small views, and this also helps then the model to generalize to details and to the full picture. And those are then also run through the model. The representation is created, and then we calculate the loss from it. And yeah, now to the results. So you see here again, we have here MoCo version 2, SimCLR like a bigger version, a much bigger version. Here we have the supervised data, and SWAV is getting closer than SimCLR and MoCo to the supervised set levels, which I guess is very interesting. Nevertheless, we have here the same trend that the models have to be a little bit bigger, that this gap is closed or almost, or is getting smaller. And here we have the numbers again. Here you see from the names that these were like older setups. This is already then here contrastive setups. And here you see this boost is quite something. So it's 4%, which is not bad for ImageNet. And the supervised on top here is like just a little bit less than 1% lower. And yeah, if you think about, I guess for ImageNet, it's maybe not the best example. I guess these methods then really shine when you have a lot of unlabeled data, where getting labeled data is very costly or maybe not available in the quantities you needed. you can easily then use approach from here, pre-train your network, and then just use a couple of labels to really push it to the same level. And yeah, now I'll look into the future. And yeah, the interesting thing is now we talked about these contrastive setups, and for natural language processing, there was like in the last 2 years, like a huge trend or a huge, it was a huge topic to pre-train your networks. And this it's like called language model pre-training. And I guess the most famous examples are the BERT model or the GPT-3, which was a couple of months ago published by OpenAI. And in the end, what OpenAI here did too, and this is from OpenAI published research, is they applied these techniques from those huge language models on images, which I guess is a very interesting approach. And what they did here is, and this is like a possible future of those self-supervised learning approaches. And yeah, in the end, you will see in a minute that this approach is like kind of maybe very simple, but very demanding on terms of the hardware. And what they did is like they used images and they had to downsample them because the full resolution would be too much for getting that working. And then when they downsampled it, they just transpose it or rearrange it into a vector. So you have like a vector of the whole image. So you see here first row, second row, third row, and then they train it, like I mentioned before, like a language model. And the language model is predicting. So you feed in this point and it has to predict the next point and the next point and so on. And so this is the normal language model training objective. And here you see the BERT training objective, which is the same, except that the model has to predict something in between. So you give it here this sequence with this crossed out, and it has to predict that. So the pre-training is kind of very simple. You don't contrast images with each other. You don't generate views. You just hand over the linearized image and tell the model, predict the next pixel in the line or predict the pixels in between. And when you train a model like that, they found out that the intermediate or the representation of the layers at the end can be used and also for classification. And then we have also our embedding. This is what you have seen before. At the output of the model, we get a vector, and we can here use also a vector intermediate from the output head. And yeah, this is a very, very interesting approach. It has some drawbacks, but we will discuss them on the next slide. And what they did then with those models is they feed in some input and let the model finishing up the image. And I guess the interesting part is if you have a look here, especially this one here with the cat, where you see there could be like a piece of paper or something. It's finishing up the image with possibilities which are not like totally off. Yeah, some look maybe strange, but they're not like they're still okay. Yeah, they're very nice. And also for the other things, here this is like I don't know, butterfly elephant or an elephant with a butterfly colored skin. And you see, this looks still reasonable. And this model learns that just by being trained by predicting the next pixel, which I guess is very interesting. And just to finish that up with the numbers is here you have our SimCLR from before and here the MoCo. And you see this approach on 64 times 64 pixels, because we have to use smaller sizes, otherwise we need too much GPU RAM, has a reasonable accuracy. This is not bad. The only bad thing is this is what you see here is the parameter count. So this model are super huge if you compare it then to the SimCLR approach or the MoCo approach. Yeah, I guess in this case it's a normal ResNet 50 or a little bit bigger ResNet, and this is the drawback. But there has been released interesting work. I mean, the problem here with the transformer is, as far as I know, they use the standard transformer. This is very memory and calculation intense setup. And there are other ways where you can use like what's the word now? Attention mechanism, which is optimized a little bit in the way. And I guess we will see more of that into the future. And yeah, I guess this in a couple of years, maybe we're not talking about these contrastive setups anymore, even though those are now the state-of-the-art models. But maybe we have also something similar like this transformer for natural language processing, but for images. But it will be very interesting to see that. Yeah, and with that, I'm at the end of my presentation. And yeah, now we can discuss some questions or yeah, talk about the stuff. And at the end of the question block, I have a small presentation and some job advertisements from the company I'm working at. So yeah, thank you very much for your attention. And yeah, just ask your questions or write them into the chat. And yeah, I'm happy to discuss them with you.
Thank you very much. That was a very interesting presentation. And we do have one question already in the chat from before. Can you see the chat?
Yeah. An example for the nonlinear transformation. Yeah. So nonlinear transformation is just, yeah, maybe the long name of a Rayleigh unit. So everything which is not linear. So nonlinear transformation, usually what they did at the beginning when the first papers came out was that they used just one linear transformation. So just one linear layer without something else. And then they used a Rayleigh on top, or I guess some people also recently used this parametric Rayleigh. But in the end, I guess a lot of nonlinear transformation will work. But in the end, it's Rayleigh or Sigmoid. And what they found is that the representation in the output space is then a little bit more better separated. In the SimCLR paper, they have in the at the end of the paper a very nice image where you see when they use this nonlinearity, the network has it a little bit easier to separate the images according to their labels. So it's getting a little bit more powerful, this output head. The hyperplane, you mean the hypersphere? Or do you mean something else with the hyperplane? Yeah, so this hypersphere, this is, I also have to admit when I read about that, I had to polish up my linear algebra again. But this was a good yeah, way to do it. And in the end, what you usually have is, because when you use like a normal computer vision setup, usually these outputs in the vector space get mapped like the model uses all the space. And with this normalization, you kind of force them to not like be stuck somewhere in space, but you force them to be exactly on this hyperplane. And this has some benefits. Like even if you use a normal setup, the big benefit is that usually when you have a label imbalance, for example, that the model is like is getting overconfident. And when you use a setup like this, or when this model gets overconfident, the kind of vector in the output stage is getting bigger and bigger. And by normalizing it, you can bring it back down on this unit hypersphere. And in the end, it can reduce a little bit the overconfidence, which is usually happening with unbalanced data and the softmax output. And like I mentioned before, this is there's like a group of called cosine losses, which are usually used for person re-identification, like on the cell phone or also on Facebook. I guess they will use something similar when you upload your photos and it already suggests the friends for you. And they always use that with some special objectives to make the gap bigger. because then if there is like a small difference in the input data and with the faces, it can happen very easily. Like you want to unlock your phone in a bright room or in a dark room, or maybe like nowadays even with a mask, and you want to still have a very accurate example. So those are setups to make you can make your classifier more robust. But if you search for cosine losses, you find a lot of interesting papers, or you can also write me an email, and I can also give you like a short list of them, or like a way where you can start and dig into that topic. And yeah, for people interested in that, I guess there's, of all of the three major things, like the SimCLR, MoCo, and SWAV, you find PyTorch implementation on GitHub. I guess I even put the links there. Maybe not for the TensorFlow one, because I'm not using TensorFlow that much, but we'll find that. So if you want to play with it, I guess that's the best way to find like a GitHub repo in like your most favorite, or based on your most favorite deep learning framework. And you should get, it should be easy to start there if you use it for like RGB image data, which is like, I guess in most of the cases the way. And yeah, then you just have to exchange the data loader, and should be quite easy to get something out of that. And yeah, so you find here I have put it there for the PyTorch stuff. Yeah, the momentum encoder. Yeah. Let's go back to that. So the theta Q is, so the theta stands here for all the parameters. And K is here for this momentum encoder. So this is, in the end, our model parameters from here. And the Q is this one here. I guess the Q is, I guess, for query. And K, I'm not sure what K stands for. I guess key does not make sense in this case. But the Q comes from query, because here you send like kind of the new image query. And like shown here, you then for the next round, this is then pushed into the queue, and the oldest two are pushed out again. And this is what I don't recall now what the M was in the MoCo setup, but I guess it's like something like 0.9 or 0.8. So like you take 80% of your old weights from this one, and 1 minus that, so like 10 or 20% of the new weights. So you have like a slow update, so to say, because this is maybe also changing faster, and maybe also sometimes into directions which are maybe not optimal at this point. So you have like a slow update with that. So it's kind of the same like with the momentum optimizer. So it's really the same formula, but it's like used between two models. I hope does that explain that to you? So one is the encoder where we make our full learning, full back propagation, and the other one is just the one we update via that rule. And yeah, I can really recommend I know from the MoCo and for the SWAV paper, the PyTorch implementations are really nice to read. So if you're interested in that, I can really recommend the code on GitHub, because actually it's quite approachable. Because yeah, the formula there will look the same, except that it's not the same type or font. And yeah, you will see it's quite easy to find the spots where this even happens.
Thanks, Michael, for the presentation. I wanted to ask, because in most of the papers, or at least the comparisons, the supervised learning was taken as kind of the baseline, or something that wants to be reached with this self-learning. How about doing some self-supervised pre-training, and then going from that point with a supervised learning method. Does that boost the performance, like the accuracy, in comparison to solely using supervised training? Or has there been any change in that direction?
Yeah. I mean, I would expect that. I mean, depends on your data. If you use like super fancy data, I guess it can be like if you don't use 3-channel RGB images, but maybe use something like satellite images with a lot of, like with 7 channels, then you have to think about how you set up your augmentation, because maybe the augmentation is different. But if you fix that, I guess in the SWAV paper, they even have the test with 1% of the labels and 10%. And even just with 1% of the labels, you get quite close to that. Maybe I can, we actually can have a look at that. So I should have put that into the slides. And so in the end, I guess, if you have a proper way to do data augmentation, which is for the normal images already there, you should expect like a quite reasonable boost.
Yeah, exactly, because you know, starting every time from a random distribution kind of weights for some network is different, or more prone to give you less or worse accuracies than kind of starting with some weights that have been learned already on the data itself without some augmentation.
Yeah.
But
definitely,
that's at least my idea.
So just let me, where is it? Let's look for 1%. Here you have it. And I guess this is quite, so.
Okay, so basically, if I have a small data set, it is better to use self-supervision than to use supervised methods, right? Or how is it to be understood?
No, what they show here is, as far as I understood, they used here ImageNet, and they trained it just here. The supervised method was just trained on 1% of the labels. If you do the same but used all of the data without labels and just take 1%, you have almost double the type 1 accuracy. So in that case, like what you mentioned, if you have like a big pool of data, you have no clue about the labels. This looks very promising, I would say. I mean, you always have to be careful. Not all the data is like ImageNet, but I guess that's a way to go to get what you mentioned, to get weights for your pre-trained model, which are better than the usual ImageNet pre-trained weights, because they are like fitting to your domain of image data.
Awesome, great, thank you.
And they even have, I guess they have even pre-trained net weights there, but it's just for ImageNet. So I guess you will have for sure the most boost when you have like a domain which is not similar. I don't know what I can think of. Like in my case, it's medical images, but I guess there are a lot, like if it's a very specific domain dissimilar from ImageNet, I guess you will this can be very beneficial.
Awesome, great, thank you.
Do we have any other questions?
Maybe until then I can load the website, then you see some nice animations from this transformer model filling up the image data, if it loads now here properly. And yeah, feel free to ask questions, or we can also like discuss points. And yeah, if there are no questions, I have like a small intro to what I'm doing in my daily job, and two job advertisements for you guys if you're interested and looking for a new opportunity. but yeah, we can still discuss. So because I guess I was a little bit faster than expected with talking during my presentation.
I think why don't we go ahead and move on, and then maybe another question comes
Yeah.
as someone has some time to think a little bit.
Perfect. Then I go back to presentation modes. So yeah, so a little bit of what I'm doing in my daily work, and after that, the job advertisements. So I'm working at Context Flow, and we at Context Flow, yeah, we were founded in 2016. We have 4 co-founders. We originated at the Medical University in Vienna, then we're supported by the Technical University in Vienna, and yeah, our work started out in a project called Krishmoy, and yeah, we want to solve the challenge, or we want to solve a challenge in radiology because there's an increasing workload at the radiologist, and there's a global radiologist shortage. So there are less people who can review CT data or MRI data, and also the work is getting more complex. And because of that, we developed like a system which supports the radiologist during his work. And in the end, it is a 3D search image. What you see here in the background, where we load in the 3D scan, then generate prediction heat maps of different disease patterns. Here you see the top 3. Then our system also looks for similar things or similar cases, also based on a similar setup what you have seen before. So we feed this part into a model, generate an output vector, then we compare them in a special way, and then we also show the radiologist like reference content and also similar cases. So this is like of a system which supports the radiologist in his workflow to make better diagnosis for the patient. And here you see our team. So we're like 17 plus employees. So we're growing also because with COVID we also have to work. Our workload increased because we want to also give the system to radiologists working on COVID and related diseases. So we have a lot to do currently, and this is why we're also looking for new people. And here you see in our technology team, there we're looking for a senior deep learning team lead for full-time position, and we're also looking for an IT project manager full-time. And if you have questions, feel also free to approach me. I can tell you a lot of details about the deep learning position, a little bit of the IT project manager position, but anyway, you find the detailed description on contextflow.com/jobs. And for questions, you can ask me or write an email to jobs@contextflow.com. So, and yeah, so this was my final presentation. So if you have questions about the presentation before or context flow or the open positions, also feel free to ask me or approach me.
Out of curiosity, with Corona, what have you guys found on your side? Has there been a higher demand for your image analysis and software program?
Yeah, so exactly what you said. I mean, then our customers or our project partners were approaching us. If we also can do something in that direction, we also already planned also something in that direction. We also have a COVID classifier, which is already deployed at some hospitals to test in there in projects with our cooperation partners. And in the end, like the system we had before is classifying the diseases based, or is classifying patterns which are assigned for a disease. And those patterns are kind of similar for COVID. So our system can support a COVID diagnosis also. I mean, it's still all in development, and it's not. So this is still an ongoing project. But we saw a higher demand, so it was a lot of more work also because we had to handle the data exchange and stuff like that. And our data files are quite big, so this was always a a lot of work to do.
Of course, but it's good to see that Context Flow and us at Anyline, we're all doing our part to support the pandemic and to move forward from this. So that's great to hear.
Yeah, it's like you have like a one-to-one connection to what you like see in the media or experience yourself. Yeah, so it's like it's good to have something like that at work that it's beneficial to society and can help in a not so nice situation.
Yeah, I couldn't agree more. I think that's really great. So I think we're close to the end. If anyone has any final questions, this is your time. Forever hold your peace. Okay, well, Michelle, I just want to say big thanks for your presentation today. It was incredibly interesting, and thank you everyone to ask questions and for engaging. We'd love to have you again sometime, but for everyone, thanks again. If you have any ideas also for presentations in the future, please reach out to me. We're happy to have the community also engage and present as well. So thanks again, Michael. Thank you, everyone. And I hope everyone has a wonderful evening.
Thanks, Michael. Bye.
Bye, everyone.
Thank you too.
Thanks a lot.
Thank you very much.
Bye. I guess we will then also distribute the slides, right? But we can.
Yeah, if you could send me the slides, that would be great.
Like
yeah, and
PDF
then
format.
Yeah, PDF is fine. And as I said, Jan will put together a blog post. Please correct me if I'm wrong.
No, it's true. It's true. But compared to the last one, it won't be the next day because there's quite a lot of stuff happening. We will condense it to a nice blog entry, and we'll also place backlinks to you. And it would be kind of nice if you could share it among your social media channels. Then, but we stay in contact anyway, and can discuss this then in the following days or next week.
Yep, you just write me an email, and then I can also send you the slides, and then we can then I can give you the information you need.
Yeah, super nice. Thank you very much.
Yeah. Oops, sorry, that's my dog. So thanks so much, then. Have a good evening, and yeah, we'll talk soon after you and Jan and me will all keep in touch.
Awesome. Yeah, thank you very much. Then have a nice evening, and talk to you soon.
Yep.
Bye.
Bye.
Thank you. Bye-bye.